Hello and welcome to the session of. In this chapter, we'll be learning about the different sources of water and its application and its treatment method. Let us see, let us have an introduction. Why we need to study water and its different treatment. Water is a polar inorganic compound that is at room temperature, a tasteless and odorless liquid, which is nearly colorless with a hint of blue. It is the universal solvent which covers 71% of the Earth's surface, mostly in the form of seas and oceans and in the form of groundwater. The pH of pure water is 7, but when the rainwater falls on the surfaces and get accumulated in the form of rivers, lakes, etc., it comes in contact with the several mineral oxides, sulfates, and carbonates or dissolved gases. As a result, it gets contaminated, and because of these impurities, the characteristics of water is changed. About 6,800 gallons of water is required to grow a day's food for a family of 4. Hence, it is the need to purify and treat water to remove these kind of impurities. Because water is nature's most wonderful and abundant and useful compound. It is not only essential for the lives of animals and plants, but also occupies a unique position in the industries. Hence, it is widely used in drinking, bathing, sanitary washing, irrigation, firefights, and air conditioning, and also in the production of industrial material. Water is present in three forms: solid, liquid, and gas. When solid converts into liquid, that process is known as melting. When liquid converts into solid, that is known as freezing. When liquid is converted into gaseous phase, that is evaporation. When gas is converted into liquid phase, that is called as condensation. And the glaciers experience a particular form of sublimation called ablation. Therefore, when solid is converted into gaseous phase or the gaseous is converted into solid phase, this is called as sublimation. This is a process wherein the snow and the ice of glacier slowly begins to turn into vapor. So gaseous, when converted to solid, it is called desublimation or deposition. Sources of water. Water is obtained from rainwater, surface water, groundwater, and the surface waters are such as lakes, ponds, rivers, streams. The groundwater forms open wells, tube wells, springs. Types of impurities. The different types of impurity present in water are mainly chemical impurities, biological impurities. Chemical impurities are in the form of dissolved salts and gases, and colloidal impurities and in the form of suspended impurities. The biological impurities are in the form of microorganisms and pathogenic bacteria. The other type of water impurity is physical impurities. Physical impurities include the change in color, turbidity, change in taste and odor. Chemical impurities. Suspended particles. The impurities present in water in the form of suspended particles or colloidal particles or dissolved salts and gases form. Suspended particles are the inorganic salts like sand particle, rocks, pebbles, mining waste, lime and other sludges, oxide dust, fly ash, flue washings, etc. The organic salts such as industrial waste or the domestic byproduct, plant and animal particles, etc. The other type of suspended particles are as which that settles at the bottom of the container due to the gravity when kept for longer periods. In case of colloidal particles, the colloidal particles are the inorganic material like clay, iron, manganese, peats, etc. There can be some organic materials also like acids, natural organic macromolecules and particles, industrial waste from, for example, China, clay or paper processing. A component of sewage solid also form colloidal particle. These colloidal particles are soluble in water at slightly higher temperature, and at room temperature the water looks dirty but you cannot see the colloidal particles. The dissolved salts and gases are the inorganic salts like calcium, magnesium, inorganic salts of chloride, nitrate, and sulfate. The organic salts are also dissolved salt in the form of dissolved salts and gas, like humic acid and fulvic acid. Pesticides and detergents are present in water in the form of dissolved salts or gases. Biological impurities. The biological impurities are microorganisms and the pathogenic bacteria. The microorganism can be an insect, larvae, water lice, etc., which breed in large number where food is plentiful. The pathogenic bacteria are the aquatic plants floating and rooted like algae, viruses, bacteria, protozoa, etc. Water are of two types, soft water and hard water. Soft water forms good lather with a soap solution and does not contain any impurities in it, whereas the hard water does not form good lather with soap solution and contains the impurities in the form of chemical or biological compound. Hard waters are of two types, temporary hardness and permanent hardness. Temporary hardness contains the carbonates and bicarbonate salts of calcium and magnesium and can be removed by simple boiling the water, whereas the permanent hardness contains the chloride and sulfate salts of calcium and magnesium, and it requires chemical treatment to remove the impurity from the water. The different types of dissolved salts present in permanent hardness and temporary hardness are: temporary hardness salts are magnesium carbonate, calcium bicarbonate, magnesium bicarbonate, and the permanent hardness salt are calcium sulfate, magnesium sulfate, calcium chloride, magnesium chloride. 1 liter. Units of hardness. The different units of hardness are degree Clerk, degree French, parts per million, and milligram per liter. Degree Clerk is the number of parts of calcium carbonate equivalent hardness per 70,000 parts of water. Therefore, 1 degree Clerk is equal to 1 part of calcium carbonate equivalent upon 70,000 parts of water. Degree French. It is the number of parts of calcium carbonate equivalent hardness per 1 lakh part of water. Therefore, 1 degree French is equal to 1 part of calcium carbonate equivalent upon 1 lakh parts of water. Parts per million. Number of parts of calcium carbonate equivalent to hardness per 10 lakh parts of water. Therefore, 1 ppm is equal to 1 part of calcium carbonate equivalent upon 10 lakh parts of water. Milligram per liter. Number of milligram of calcium carbonate equivalent hardness per liter of water. Therefore, 1 milligram per liter is equal to 1 milligram of calcium carbonate equivalent upon 1 liter of water. Let us see the conversion between these units, that is the relationship between the different units of hardness. 1 ppm is equal to 1 milligram per liter. 1 ppm is equal to 0.1 degree French and 1 ppm is equal to 0.07 degree Clark. Now if you want to convert from French degree, that is 1 degree French is equal to 10 milligram per liter. 1 degree French is equal to 0.7 degree Clark and 1 degree French is equal to 10 ppm. Similarly, 1 degree Clark can be converted into other three as 1 degree Clark is equal to 14.3 milligram per liter. 1 degree Clark is equal to 1.43 degree French and 1 degree Clark is equal to 14.3 ppm. To calculate the hardness of water, first we need to know the equivalent weights or the atomic weights of the different elements which forms the dissolved salts present in water. For example, calcium, so its atomic weight is 40, magnesium atomic weight 24, sulfur atomic weight 32, oxygen atomic weight 16, carbon 12, hydrogen 1, chlorine 35.5. Hence, if we want to calculate the molar mass and the equivalent weight, we can calculate with respect to the atomic weight of each of the element. So the calculation of equivalent of calcium carbonate is 100. Molar mass 162, equivalent weight 81. Magnesium carbonate MgHCO3 twice 146 molar mass and equivalent weight is 73. So, the difference in the molar mass and the equivalent is that molar mass is the exact calculation of all the atomic weights of the element present in this formula. And the equivalent weight is divided. That means the molar mass divided by its oxidation state. So, another magnesium carbonate MgCO3 molar mass 84 and equivalent weight 42. Calcium chloride CaCl2 the molar mass is 111 and the equivalent weight is 55.5. Magnesium chloride MgCl2 molar mass 95 and equivalent weight is 47.5. Calcium sulfate CaSO4 the molar mass is 136 and the equivalent weight is 68. Magnesium sulfate MgSO4 molar mass is 120 and equivalent weight is 60. Let us see what are the disadvantages of using the hard water in different fields. The hard water, when used in domestic purpose, for industrial purpose, for steam generation, and for laundry and concrete making, it creates a problem and cannot be directly used in all these applications. Because when we use hard water in domestic use, for example, for washing, bathing, cooking, and drinking, it will affect our digestive system, our body. When we use hard water in industrial use, for example, in case of textile industry, pharmaceutical industry, sugar industry, dyeing industry, paper industry, laundry, etc., again it will create an adverse effect because of the impurities or the dissolved salts present in the water. And if we use in steam generation, for example, in steam generation, if hard water is used, then 100% efficiency is not achieved due to priming and foaming of water. In case of laundry and concrete making, the hard water will affect the hydration of cement and creates the stains of dissolved salts also when dry, or when present in fabric. The effect of hard water in the different fields. Let us see one by one. Suppose in domestic use, as we have seen that in domestic use, we use it for washing purpose. So if we use hard water, then it will not produce the good leather with the soap solution, and the salts will be precipitated out, and there will be wastage of soap. If we use the hard water for bathing purpose, it will produce a sticky scum on the bathtub also and the body also and affects the skin. If we use the hard water in cooking, then more fuel is consumed while cooking as the boiling point of water is elevated. And also the food is not cooked soft. If we use the hard water for drinking, it will affect the digestive system of our body. As you can see here, the use of hard water, if used for bathing, then the skin is allergic as shown in the image. Similarly, due to the hard water, the tap and the shower parts are covered with the dissolved salts. If we use hard water in industry use, suppose in textile industry, pharmaceutical, sugar industry, dyeing industry, paper industry, laundry, everywhere the water is, and if in industry the water is hard, then suppose in textile industry the dissolved salts adheres to the fabric and do not produce the exact shade of the textile material. If the hard water is used in sugar industry, it will causes difficulties in the crystallization of the sugar at the end. Dyeing industry. If hard water is used in dyeing industry, they will react, the impurities or the dissolved salts will react with the dyes, forming undesirable products which gives the impure shades to the textile material. If hard water is used in paper industry, then it will affect the finishing and the color of the paper, and the dissolved salt appears as spots on the finished paper. If the hard water is used in pharmaceutical industry, then in the manufacturing of drugs, medicines, it will affect the quality and purity and produces certain undesirable byproduct. Hence, the hard water cannot be used in domestic and industrial applications. The effects of hard water creates scale and sludge formation. It creates priming and foaming of water. There is also formation of chances of caustic embrittlement and boiler corrosion. For example, we can see here in the image, because of the scale and sludge formation, the inner diameter of the pipeline or the particular apparatus are choked up because of the formation of scale and sludge. Because of priming and foaming, the exact surface of the water cannot be judged and also the steam cannot be generated. Because of caustic enrittlement, boiler corrosion, if the pH of water is more and if NaOH sodium hydroxide is used to maintain the pH, then that caustic is accumulated at the joints as shown here in the image in the form of white salt. Scale and sludge formation. The scales are generally hard adhering coating inside the boiler on the walls and the bottom of the boiler. As shown in the figure, this is the scale which is formed on the inner walls of this material. The scales are formed due to the salts having higher solubility in cold water. For example, decomposition of calcium carbonate. Calcium bicarbonate is converted into calcium carbonate which get deposited on the side walls of the material. This calcium carbonate ultimately when reacts with water forms calcium hydroxide and carbon dioxide. The second reason is by hydrolysis of magnesium salt. Magnesium chloride when react with water, it forms magnesium hydroxide and 2 moles of HCl. That means the pH of water becomes acidic. Third reason is the presence of silica. The deposits as calcium silicate or magnesium silicate and sticks firmly on the inner side of the boiler surface, which is very difficult to remove. As shown here, the walls of the boiler is shown and the difference in the formation of scale and sludge. Sludge remains present in the water and get accumulated at the areas of where the flow rate is low and colder region. Whereas the scale are hard adhering coating which just stick to the walls of the boiler only. Removal of scales and sludge. Scales, if are brittle, can be removed by thermal shock, that is, by heating the boiler and then sudden cooling with cold water. If the scales are hard and adherent, then they can be removed by using chemicals such as 5 to 10% of hydrochloric acid, which can dissolve the scale salts. The sludge, which are soft and slimy, can be used or can be removed by using the soft water in boilers or by frequent blow down operation, that is drawing off a portion of the concentrated water that which contains large amount of dissolved salts and replacing it with fresh water. The scale treatment by blow down operation can be done by adding colloidal conditioning, that is low pressure boiler kerosene, tannin, agar agar, then by adding phosphate conditioning method, for example in high pressure boilers by adding sodium phosphate, then carbonate conditioning, for example in low pressure boiler by adding sodium carbonate, calgon conditioning by adding of calgon sodium hexametaphosphate. The scale treatment can also be done with the help of sodium aluminate or another method, electrical conditioning, that is immersing a sealed glass bulb containing mercury connected to the priming. In the priming process, priming is the process where steam is generated from water and steaming is rapidly done. Then some of the particles of liquid water are carried along with the steam. This process of wet steam formation is called priming, as shown in the image. The causes. The presence of large amount of dissolved salts cause priming. Then if there is sudden boiling, improper boiler design, high velocity of steam, sudden increase in steam production. This can lead to priming in the water. The effects of priming. The dissolved salts are carried by the wet steam to superheated and turbine blades where they get deposited as water evaporates and hence reduces the efficiency of steam and boilers. Foaming. The formation of persistent foam or bubbles which do not break easily is known as foaming. Foaming is influenced in the presence of substances like oil or grease which greatly reduce the surface tension of the water, alkalis present in the water, clay or organic matter present in the water, finely divided particles of sludge present in the water. As we can see here in the image, there is foaming created in the boiler on the surface of the water. And because of this formation of foam, we cannot judge the exact gap between the surface of the water and the surface of the boiler diameter. So this we can see with the help of an example, that is how the water is fed into boilers and what are the effects if the hard water is filled in the boiler water through this video. Explain boiler feed water. Hence, we can see how the hard water affects the boiler condition and the efficiency is also reduced, and there is a formation of priming, foaming, scales and sludge, and how they affect the boiler process. Prevention of priming and foaming. Priming can be prevented through fitting mechanical steam purifier, by avoiding rapid change in the steam production rate, and by maintaining the low water levels in the boilers, whereas foaming can be prevented by adding castor oil, adding anti-foaming agents, and adding sodium aluminate. Boiler corrosion. The boiler feed water is an important part in the boiler operation, as we have seen through the video. Hence, the water feed into the boiler should not contain the dissolved impurities, because if the water contains these impurities, then during the process the impurities will react with the water and other gases, changing the pH of the water, thereby decay of boiler material takes place, which leads to the corrosion of the boiler material as shown here in the image. Therefore, boiler corrosion is exactly the decay of the boiler material by a chemical or electrochemical attack by the environment. The causes of boiler corrosion are because of the presence of dissolved oxygen in boiler water, presence of dissolved carbon dioxide in boiler water, unbalanced pH of the boiler water, and no periodic maintenance of the boiler. Let us see all these causes one by one. How the water affects the boiler corrosion. Presence of dissolved oxygen in boiler water. Dissolved oxygen if present in water, then water usually contains about for approximately 8 ml of dissolved oxygen per liter at room temperature. Therefore, dissolved oxygen in water in presence of high temperature attacks the boiler material. The iron or the material which is material of the boiler reacts with the water, and because of the presence of dissolved oxygen, it will form ferric hydroxide. This ferric hydroxide also again react with the oxygen present in the water, and it will form a rust. That means the boiler material, the walls of the boiler will corrode. To remove this dissolved oxygen from the water, we can add calculated amount of sodium sulfite or hydrazine or sodium sulfide. Thus, when we add sodium sulfide, it will react with the dissolved oxygen to form sodium sulfate. And if hydrogen is added, then also it will react with the dissolved oxygen and it will produce nitrogen gas and just water. If sodium sulfite is added, it will react with the dissolved oxygen to form sodium sulfate, which is neutral and can be separated out. Presence of dissolved carbon dioxide in water. Dissolved carbon dioxide. Carbon dioxide on reacting with water forms carbonic acid in water, which is corrosive and affects the boiler material. If the water used for steam generation, it contains bicarbonate salt. So this bicarbonate salt is converted to magnesium carbonate during the boiling, and water and carbon dioxide. So this dissolved carbon dioxide creates the boiler corrosion. To remove this dissolved carbon dioxide, we can add calculated quantity of ammonia. Thus, when ammonium hydroxide is added, it will react with the carbon dioxide and form ammonium carbonate, which can be easily removed. Third, acids from the dissolved salts. If the water containing dissolved magnesium salt liberates acid on hydrolysis, for example, if the water contains magnesium chloride salt, then it will react with water and form magnesium hydroxide and hydrochloric acid. The liberated hydrochloric acid react with the material of the boiler, that is iron of the boiler, in chain like reactions producing hydrochloric acid again and again. That is, the iron or the material of the boiler will react with this particular acid which is formed because of magnesium chloride, and The iron, on reacting with the hydrochloric acid, forms FeCl2 plus hydrogen gas. This FeCl2 again, when react with water, it will form ferric hydroxide, and again the byproduct HCl is produced in the water. Consequently, the presence of even small amount of magnesium chloride will cause corrosion of iron to large extent because of continuous formation of hydrochloric acid and changing the pH towards acidic medium. Caustic embrittlement. Caustic embrittlement is a boiler corrosion which is caused by using highly alkaline water in the boiler. During softening process in the boiler feed water, free Na2CO3 is present in small proportions. Hence, when water is heated in high pressure boiler, sodium carbonate decomposes to give the sodium hydroxide and carbon dioxide, which makes the boiler water basic due to the formation of caustic, which is sodium hydroxide. So, when sodium carbonate is added in water, it will react with water to form sodium hydroxide. This caustic water, which is basic in nature, flows into the minute hair cracks where water evaporates and the dissolved caustic soda get concentrated and get deposited at the joints and those areas which with the time increases progressively, as you can see here, thereby dissolving iron of boiler as sodium ferroate, which causes embrittlement of the boiler parts like bends, joints, rivets, etc., causing even failure of the boiler. Caustic embrittlement can be avoided by using sodium phosphate as softening agent instead of sodium carbonate by adding tannin or lignin to the boiler water, which blocks the hair crack. Also by adding sodium sulfate to boiler water. The sodium sulfate also blocks the hair crack, and caustic cracking can be prevented if sodium sulfate is added to boiler water. So the ratio is kept as 1:1, 2:1 and 3:1 in the boilers, working respectively at pressures up to 10, 20 and above and 20 atmospheric pressure. The ratio is calculated as sodium sulfate to sodium hydroxide concentration. Analysis of water. The analysis of water is done for hardness of water, alkalinity of water, dissolved oxygen, that is biological oxygen demand and chemical oxygen demand, dissolved carbon dioxide, free chlorine, silica content and total solids. Hardness of water is experimented as by determination of hardness by complexometric method or EDTA method. The principle behind this experiment is that the hardness of water is calculated by the performing the experiment of complexometric titration, where the water sample is titrated with sodium salt of ethylene diamine tetraacetic acid, that is EDTA, using an indicator idiochrome black tea, keeping the pH of water at 9 to 10 pH. The end point is change in the color from wine to red to blue. The EDTA solution complexes the calcium and magnesium salt completely and the color changes from wine to red to blue. The mechanism behind the complexometric titration is that the calcium and the magnesium salt, that is the dissolved salts, react with the EBT, that is the indicator, and forms an unstable complex which is wine red in color. And this complex, when react with the EDTA, then it will form again a big complex with calcium or the magnesium salt, which is of blue color. As we can see here, this is the process of any titration: weighing, dissolve, then transfer, dilute, pipette out, titrate, pipette, titrate, and you will get the result. The chemicals required in the experiment of complexometric titration are: first, the preparation of standard hard water. So dissolve 1 gram of pure, dry calcium carbonate in minimum quantity of dilute hydrochloric acid and then evaporate the solution to dryness on a water bath. Dissolve the residue in distilled water to make 1 liter solution. Each ml of this solution thus contain 1 milligram of calcium carbonate equivalent hardness. For preparing the EDTA solution, dissolve 4 gram of pure EDTA crystal in 1 liter of distilled water. Preparation of indicator. Dissolve 0.5 gram of idiochrome black tea in 100 ml of alcohol. For preparing a buffer solution to maintain the pH during the titration, add 67.5 gram of ammonium chloride to 570 milliliters of concentrated ammonia solution and then dilute with distilled water to 1 liter. The procedure to standardize the EDTA solution. First, rinse the burette and fill it with EDTA solution. Pipette out 20 ml of standard hard water in conical flask. Keep this volume as M1. Add 4 ml of buffer solution and 2 drops of EBT indicator. Now, titrate with the flask solution present in the flask with EDTA solution till wine red color changes to clear blue as shown in the animation. The color is changed and the titration is carried out till the color turns blue. Now let us assume the volume used by X ml. So M1V1 is equal to M2V2, where M1 is the molarity of standard hard water and V1 is the volume of standard hard water. M2 is the molarity of EDTA solution and V2 is the volume of EDTA which you are adding dropwise in the titration. Determination of total hardness. Rinse and fill the burette with again EDTA solution. Pipette out 20 ml of sample water, which is volume 3, in a conical flask. Add 4 ml of buffer solution and 2 drops of indicator. Titrate this EDTA solution with the sample solution till wine red color changes to clear blue. Again now assume the volume used is YML. So again M2V2 is equal to M3V3, where M2 is equal to molarity of EDTA, V2 is equal to volume of EDTA, which is YML, which you get through titration. M3 is the molarity of sample water and V3 is the volume of sample water, which we have taken in the conical flask. Therefore, the total hardness will be equal to M3, that is the molarity of sample water multiplied by molecular weight of calcium carbonate, which is 100, into 1 liter, that is 1000 ml, which is equal to molarity of sample water, that is M3 multiplied by 105 ppm. Therefore, the strength of hard water, standard hard water sample, that is calcium carbonate solution Mn, is equal to weight of calcium carbonate into 1000 upon molecular weight of calcium carbonate into 1000. So the strength of standard hard water will be 0.01 moles and the strength of EDTA solution, that is M2, is equal to V1 M1 upon V2, which is equal to 50 multiplied by 0.01 upon 20. So the strength of EDTA solution is 0.025 molar, where V1 is the volume of standard hard water and M1 is the strength of standard hard water. Thereby calculating the total hardness, M3 will be equal to V2 M2 upon V3, where V2 is the volume of EDTA solution, which is 25 ml, and M2 is the strength of EDTA solution, which we have calculated through standardized method, that is 0.025 molar, and V3 is the volume of sample of hard water, which we have taken as 50 ml. So the total hardness, that is strength of sample hard water, will be equal to 25 multiplied by 0.025 upon 50, which will be equal to 0.0125 molar. Therefore, the total hardness will be equal to the total hardness multiplied with the 105 strength ppm of sample hard water, which will be equal to 1012 1250 ppm. Softening of water. Softening of water is the process of removing the dissolved salts of calcium and magnesium which causes hardness in water. It can be done either by adding chemicals that form the insoluble precipitates or by ion exchange. The resulting soft water requires less soap for cleaning as the salts are removed. The only disadvantage of softening of water is that the required amount of salts for the potential health are also removed. Zeolite or permutate method. Permutate is a modern technique used to soften the hard water. It is the hydrated sodium aluminium silicate which is called permutate. These complex salts are also known as zeolite. The hard water is passed in the cylindrical vessel packed with gravel and sand and permutate. As shown in the diagram, this is the permutate or the zeolite which is present naturally, and here the layer of gravels are found. From the bottom of the tank, the wastewater is collected, and from the upper side, the soft water is collected. Through this inlet, the hard water is fed inside this zeolite or permutate. The water reaches the bottom of the cell. When the hard water is fed through this inlet, the hard water first reaches the bottom and then by passing through this gravel through the zeolite or permutate, it goes in the upward direction so that all the impurities are get trapped between these permutate, and the soft water is collected from this end. After the complete procedure, the wastewater tap is opened and rejected. The separation of impurities is followed when water passes through the gravel layer. After passing through the gravel, the water passes through the permutate or zeolite, where the cations of magnesium and calcium are replaced by sodium ions present in the tank water. Hence, when water passes through this gravel and the permutate or the zeolite layer, the cations of calcium and magnesium are replaced. As shown here, only the soft water molecules are passed through the zeolite or permutate, and the calcium and magnesium ion are replaced by these sodium ions. As shown in the animation, that the calcium ions replace the sodium ion, and sodium ion goes out with the water, but the hardness causing ion, that is calcium, are trapped in this zeolite. So if the water contains calcium bicarbonate, then it will react with the zeolite, and the sodium ion is replaced by calcium ion, and sodium bicarbonate goes into the water. Similarly, if the hard water contains magnesium bicarbonate, again the sodium is replaced by magnesium, and sodium bicarbonate is formed, which is neutral. If there is salt of calcium sulfate, again sodium will be replaced by calcium, and Na2SO4, that is sodium sulfate, is formed, which is again neutral. If calcium chloride ion is present, dissolved salts are present, it will again react with the zeolite, and the sodium will be replaced by calcium, and it will form 2 moles of sodium chloride. Similarly, if magnesium sulfate is present in hard water, it will react with the zeolite or the permutate, and the sodium ion is replaced by magnesium, and it will form a byproduct Na2SO4 again, which is neutral. If the hard water contains magnesium chloride, it will react with the zeolite, and the sodium will be replaced by magnesium, and 2 NaCl, 2 moles of sodium chloride is formed, which goes into the water. So after some time, when the zeolite is completely changed into calcium and magnesium zeolite, that is this form, then it gives the exhaust state. Then it gets exhausted. It can be regenerated and reused by treating it with 10% brine solution, that is sodium chloride solution, where the calcium and magnesium ion are again replaced by the sodium ion. So calcium zeolite, that is the sodium ion was replaced by calcium. So again, when we treat it with the 10% brine solution, this calcium ion will be replaced by the sodium ion. Similarly, the magnesium ion will be replaced by sodium ion. Merits and demerits of zeolite. Merits of zeolite processes are that it removes the hardness almost completely, that is about 10 ppm hardness. The process automatically adjusts itself for variations in hardness of incoming water, and there is no addition of any chemical or additives. This process does not allow involve of any type of precipitation, thus no problem of sludge formation occurs. Demerits of zeolite process. The outgoing water, that is the treated water, contains more sodium salt, and this method only replaces the positive ion, that is the calcium and magnesium ions, by sodium ion. Another demerit is that there is high turbidity. This high turbidity water cannot be softened efficiently by zeolite process. The colored impurity, if present in water, are also not removed and ultimately destroy the resin. Ion exchange method. Ion exchange is also known as demineralization process. Ion exchange resins are insoluble, cross-linked, long-chain organic polymers with a microporous structure having functional group which are replaceable. For example, as shown in the animation here, the hard water is fed into this zeolite or resin, and the soft water, after passing through this zeolite or resin, goes out through this pipe. Here it is a brine solution which is used to regenerate the zeolite or the permutate or the resin. So in case of ion exchange method, the resins with acidic functional group are capable of exchanging the hydrogen ion H plus ion with the other cation ion. The resins with basic functional group are capable of exchanging OH minus ion with other anions. Ion exchange resins are of two types, cation exchanger and anion exchanger. Cation exchangers are generally strong acid cation and weak acid cation, and the anion exchangers are generally strong basic anion and weak basic anion. Cation exchange resin. The cation exchange resins are usually styrene divinyl benzene copolymers which contain carboxylic group, sulfonic group, functional group which exchanges their hydrogen ions with cations in water. So the reaction will be the cation exchange resin. If there is calcium bicarbonate, then this resin will react with this calcium bicarbonate and the H plus ion will be replaced by calcium forming carbonic acid. Similarly, if magnesium bicarbonate is present, again the H plus ion will be replaced by magnesium ion and carbonic acid is formed, which goes with the water. If calcium chloride is present, the hydrogen ion will be replaced by calcium ion and HCl will be produced. Similarly, if magnesium chloride is present, it will react with the resin, that is cation exchange resin, where the H plus ion is replaced by magnesium ion and hydrochloric acid is produced. If magnesium sulfate is present, it will react with the resin and where the H plus ion again is replaced by the magnesium ion and the acid produces H2SO4. If calcium sulfate is present, it will react with the resin and the hydrogen ion will be replaced by calcium ion and sulfuric acid is formed, where all these RH ion are the cation resin. In case of anion exchange resin, the anion exchange resins are phenol formaldehyde or amine formaldehyde copolymers which contains the amino or basic functional group which exchanges their OH minus ion with the anions in water. So in the previous step where the positive ions are all replaced and the acid is formed, whether it is HCl, H2SO4, so it goes into the water. Now it is the turn where the anion will be replaced by OH minus ion. So the acid formed in the previous step will react with this anion resin and the OH will be replaced by chlorine and hence the water is pure, or that is water is softened by forming H2O. Similarly, if the acid is H2SO4, then this OH minus ion is replaced by this sulfate ion and water is softened. If carbonic acid is formed, then again the OH minus is replaced by carbonate ion and water is softened, where ROH is the anion exchange resin. In this diagram, it is shown first the water is fed into the cation exchanger. The impure water, when fed into cation exchanger, it passes through the resin and the acids are formed, whether carbonic acid, sulfuric acid or hydrochloric acid. This acidic water is then passed through this pipeline to the anion resin. So in anion resin, the negative ion, that is the anions, will be replaced by OH minus ion, that is the hydroxide ion, by passing through this anion exchanger. And the neutralized water, softened water, is then passed through this steam jacket, where if there is any dissolved carbon dioxide, then it is exhausted out through this outlet and the soft water, that is the demineralized water, get collected at the bottom through this outlet. Degeneration process of cation exchanger and anion exchanger. When cation exchanger and anion exchanger stop producing H plus ion or OH minus ion, they are said to be exhausted. The exhausted cation exchanger is regenerated by passing dilute sulfuric acid through it or dilute hydrochloric acid through it. So, the calcium ion and the magnesium ion will again be replaced by H plus ion of the acid and the cation exchange is again regenerated. The exhausted anion exchanger is regenerated by passing a dilute solution of sodium hydroxide through it. Therefore, the anion exchanger, which is exhausted and contain the sulfate or chlorine ions, they are replaced by the OH minus ion and the anions are again regenerated. As shown in the image, the anions are replaced again and regenerated again. Merits of ion exchange process. The process can be used to soften highly acidic or alkaline water. It produces water of very low hardness, say 2 ppm. It is very good for treating water for use in high pressure boilers. Demerits of ion exchange process. The equipment is costly and more expensive chemicals are needed. If water contains turbidity, then the output of the process is reduced. The turbidity must be below 10 ppm. If it is more, then it has to be removed first by coagulation and filtration. Lime soda method. Lime soda softening method is a water treatment process where calcium hydroxide or lime water and soda or sodium carbonate is used to soften the water by removing calcium and magnesium ions. The basic principle behind lime soda method is that lime, that is calcium hydroxide, and soda, that is Na2CO3, are chemical reagents which is added in order to precipitate the dissolved salts of calcium and magnesium as calcium carbonate and magnesium hydroxide. The precipitated calcium carbonate and magnesium hydroxide are then filtered off. So in this process, the hydrated lime, when added to hard water, reacts with the temporary hardness carbon dioxide, acids, bicarbonates, and alums and raise its pH level and precipitate the ions, which causes the hardness. In lime soda method, the coagulants such as aluminum sulfate, and sodium aluminate are also added, which helps in the formation of coarse precipitate. From both the types of method, the hot lime soda process requires hardly 15 minutes and it is more economical, while cold process requires several hours. As shown in the diagram, the hard water or the raw water is fed from this inlet where the pedals are present, and from the left hand side the chemicals, that is the soda plus lime and the coagulant, are fed into this chamber. Here there is a wood fiber filter which will not allow to pass the other impurities present in the hard water. When the water enters through this inlet, then the through with the help of driving belt the pedals are rotated so that the chemicals are evenly distributed in all the parts of the or the in all the area of the chamber where the hard water is present. The dissolved salts and the dissolved gases react with the chemicals and get accumulated in the form of sludge at the bottom, and the soft water passes through this wood filter and get collected from this outlet as filtered softened water outlet. At the end of the process, the sedimented sludge is removed from at the bottom through this outlet. So in hot lime soda method, also easily remove the dissolved gases like oxygen and carbon dioxide. Treatment with lime water. When lime is added to hard water, it will remove the temporary hardness of calcium. That is, calcium bicarbonate will react with the lime and form calcium carbonate and get settled down at the bottom of the chamber. Also, the magnesium bicarbonate react with the lime and form magnesium hydroxide and calcium carbonate. For removal of permanent hardness, magnesium chloride, magnesium sulfate, magnesium nitrate, if present in water, they will react with this lime and form magnesium hydroxide salt, which is get accumulated at the bottom of the chamber. It also forms calcium chloride, calcium sulfate, and calcium nitrate. Because of lime, the dissolved carbon dioxide is also removed from the water because the carbon dioxide react with the calcium hydroxide, that is the lime, and forms calcium carbonate. Treatment with soda. Removal of permanent hardness of calcium. If soda is added to the hard water in lime soda method, it will react with calcium chloride, calcium sulfate, and calcium nitrate to form calcium carbonate, along with sodium chloride, sodium sulfate, and sodium nitrate. Advantages and disadvantages of lime soda method. Advantages: it is very economical process. To a certain extent, the iron and manganese impurities are also removed. Alkaline nature of the water reduces the pathogenic bacteria present in water, and less amount of coagulants are required. The disadvantages of lime soda method are that the hardness of softened water is about 50 to 60 ppm, which is not good for use in high pressure boilers. Careful operations and skilled supervisions are also required for the economical and efficient softening of the water. Disposal of large quantity of sludge formed during the process is again a problem. Osmosis. When two solutions of unequal concentration are separated by a semi-permeable membrane, the flow of solvent takes place from dilute or low concentration to high concentrated site. This is called osmosis. As we can see here in the animation, low sugar concentration compartment with high water concentration, and the another one is high sugar concentration with low water concentration. Between the two cells, there is one semi-permeable membrane which separates the two compartments. So, in case of osmosis, the flow of solvent takes place from dilute or low concentration to higher concentration side. Reverse osmosis. Reverse osmosis is a process in which the pressure gets greater than the osmotic pressure is applied on the high concentration side of the membrane. Thereby, the flow of solvent moves from the concentrated side to the lower side across the membrane. Here we can see it is exactly the opposite of osmosis process. The flow of the solvent is from the higher concentration to the lower concentration part. Hence it is called reverse osmosis. Water flows from the more concentrated side of the membrane to the less concentrated side. The fresh water produced is called the permeate, and the concentrated water left over is called the waste or the brine. The membranes used are cellulose acetate, polymethyl acrylate, and polyamide polymers. A semi-permeable membrane used in reverse osmosis has small pores that block the contaminants but allow the water molecules to flow through it. For example, there are different types of membrane as shown here. In the reverse osmosis, the pressure bar is 30 to 60 atmospheric pressure and the member pore size is less than 0.001. Similarly, for nanofiltration, it is 20 to 40 pressure bar and 0.001 to 0.005 membrane pore size in micrometer. The membrane has small pores and the pores are able to pass only few molecules as per their membrane pore size. So as shown here in the example that the black particles are the bacteria, green are proteins, purple is sugar, red is mineral and sky blue color is of water. So we can see here in reverse osmosis only the water is coming out and rest the bacteria, protein, sugar, minerals are not passed from the membrane. Advantages of reverse osmosis method. Advantages: ionic as well as non-ionic, colloidal and high molecular weight organic matter is also removed in the RO system. Maintenance cost is almost entirely on the replacement of semi-permeable membrane. The lifetime of membrane is quite high, that is about 2 years, and it removes 98% of the dissolved solids, which makes it healthier to drink. The only disadvantage in the reverse osmosis system is that the salts needed for the body system, for the digestive system, are also removed from the water. Characteristics of drinking water. It should be colorless and odorless. It should be pleasant in taste. Its turbidity should be less than 10 ppm. It should be free from the dissolved impurities such as lead, arsenic, chromium, and manganese salt. Its alkalinity should not be high and the pH should be in the range of 7 to 8.5. The total hardness should be less than 500 ppm. The drinking water should also be free from the disease-producing microorganism and also should be free from the dissolved gases like hydrogen sulfide. It should be reasonably soft and should be perfectly cool. Treatment of drinking water. The treatment of drinking water can be done by removal of suspended or colloidal particle and by removal of microorganisms or pathogenic bacteria. The removal of suspended and colloidal impurities can be done by screening, sedimentation, coagulation, and filtration method. Whereas the removal of microorganism and pathogenic bacteria can be done by boiling the water, by chlorination method, by disinfection through ozone, or by adding chloramine, or by adding the bleaching powder. Screening. Screening is the first stage of water treatment process where It is the process of removing the floating impurities from the water by passing the water through different screens of different size. As shown in the image, there are different screens. This is the screen 1A, here is the screen B, and here is another screen C. So screening removes large objects like plastic, bottles, sanitary items, papers, damaged equipment. Sedimentation. Sedimentation is the process of allowing the water to stand undisturbed in the big tank about 5 meters deep, where most of the suspended particles settle down at the bottom due to the force of gravity for longer period of time. The clear water is then drawn from the tank through the outflow or the pump. As you can see here in the animation that the particles are settling down at the bottom of the tank because of the force of gravity. Hence, the retention period of water in a sedimentation tank is large. This is a sedimentation tank where the water is decanted from this outflow and these are the sludge scraper arm where the sludge collection are then rejected through this end. From here, the water is fed into the chamber of the sedimentation tank. Sedimentation with coagulation. If the water contains the fine clay particles or colloidal impurities, then sedimentation with coagulation is carried out for removing the impurities. Coagulation is a process of removing the colloidal impurities by addition of requisite amount of chemical which is called as coagulant to water before sedimentation. As shown in the image, in the hard water, the coagulant is added where the impurities are present. The coagulant will react with these impurities and forms a precipitate or a flock which tap the other impurities also like this. And with the period of time, all these coagulated impurities are then precipitated and trapped and settled at the bottom of the tank. The coagulant when added to water forms an insoluble gelatinous flocculant precipitates which descend through the water, adsorbs and entangles very fine suspended impurities also forming bigger flock as in the second image, which then settle down easily during the retention period of the sedimentation. Coagulation principle. The coagulant have opposite charges to those of the suspended solids. Hence, when added to water, they neutralize the negative charges on dispersed non-settleable solid such as clay and organic substances. Once the charge is neutralized, the small suspended particles are capable of sticking together and form flock which stick to other fine clay particles and settle down at the bottom of the tank during retention period. As shown in the animation, slowly the coagulant will attract all the organic substances such as clay and other material and will form a gelatinous flock like this and becomes bigger and bigger and ultimately settle down at the bottom of the tank. The most commonly used coagulant are alum, sodium aluminate, copperas or ferrous. Filtration. Filtration is the process of removing colloidal matter and the suspended matter along with the most of the bacteria, microorganisms, etc. by passing the water through a bed of fine sand and other proper sized granular material as filters. As shown in the diagram, the filtration tank consists of different layers. One is gravel, one is sand, and the another one is finely divided sand. The hard water is passed through this inlet after coagulation method and the particles get accumulated or collected in between the sand and gravel and the soft water is collected from the bottom. Usually, the filtration is carried out by using a sand filter which consists of a thick top layer of fine sand placed over coarse sand layer and gravels. During the filtration process, the sand pores get clogged due to retention of impurities in the water. Hence, the water treatment process include different steps. That is, the raw material is mixed with the coagulant and passed to the coagulation tank, then through the flocculation tank, and then to the sedimentation tank, where the sediments are settled down at the bottom of the tank and the water is passed to the another step or the another tank where filtration takes place. After passing the water through the filtration bed, it is then disinfected and then passed to the distribution or the home consumption center. Removal of microorganism and pathogenic bacteria. Water after passing through sedimentation, coagulation and filtration operation still contains small amount of bacteria and diseases producing microorganism. Hence, the process of destroying or killing the disease producing bacteria, microorganisms, etc. from the water and making it safe for use is called disinfection or sterilization of water. The chemicals or substance which added to the water for killing the bacteria are known as disinfectant. This can be done by following methods. Number 1, by boiling the water for 10 to 15 minutes. 2, by adding the bleaching powder. 3, by chlorination. 4, by adding chloramine. And 5th, disinfection by ozone. First method, sterilization method. The sterilization method can be physical or chemical. Physical method include treatment through heat, radiation and filtration. Whereas the chemical method include by passing gas or liquid form of the different types of chemical, for example, formaldehyde, ethylene oxide, alcohol, halogen, phenol, aldehyde. Whereas in case of physical method, the heat supply of heat can be done in the dry condition or the moist condition, where in the dry condition incineration or drying in oven is done for sterilization, whereas for radiation ionizing and non-ionizing rays are used, that is X-rays, gamma rays, cathode rays, or non-ionizing rays such as ultraviolet rays is used for sterilization. For filtration, different membranes or the sheets are used, for example, asbestos sheet, membrane sintered glass. In case of moist condition, when the heat is passed, then it is done through pressurized steam system or boiling water or water heating or pasteurization. Second, by adding bleaching powder. In this method, approximate 1 kg of bleaching powder per 1000 kiloliters of water is mixed with water and then it is allowed to stand and for undisturbed for several hours. So, the calcium hypochlorite will react with water to form calcium hydroxide and chlorine gas, and the chlorine gas generated in water reacts with the water to form HCl and HOCl. This hypochlorous acid will then react with germs and kill the germs because this hypochlorous acid will break into HCl and nascent oxygen. This nascent oxygen is responsible for killing the germs. The drawback for using the bleaching powder is that it introduces calcium in the water, thereby making it hard again. Only a calculated amount of bleaching powder is to be used because slight excess amount can give bad taste and smell to the treated water. And the third drawback is that it deteriorates due to the decomposition during the storage. By chlorination. Chlorine gas, by passing chlorine gas, is a very good disinfectant which can be bubbled in the water. In this process, the calculated amount of chlorine gas is passed through the water in order to destroy the pathogenic bacteria, which is called chlorination. The chlorine reacts with the water and generate hypochlorous acid and nascent oxygen, which act as a powerful oxidizing agent and kills the bacteria. When chlorine directly reacts with water, hypochlorous acid is formed, which breaks into HCl and nascent oxygen will react with the germs and kill the bacteria. The factors affecting the efficiency of chlorine are the time of contact, temperature of water, and pH value of the water. Time of contact. The number of microorganisms destroyed by chlorine per unit time is proportional to the number of microorganisms remained alive. Hence, the death ratio of microorganism is maximum to start with and it goes on decreasing with time. Temperature of water. The rate of reaction increases with the increase in temperature. Hence, the death of rate of microorganism by chlorine increases with the rise in water temperature. pH value of the water. Lower is the pH, that is between 5 to 6.5 value of the water, then the contact period of chlorine with water is also less to kill the same percentage of organisms. The advantage of using the chlorine gas to kill the germs and bacteria is that if it is effective and economical, it requires very little space for storage and can be used at low as well as high temperature. Whereas the disadvantage of using the chlorine gas directly by passing into the water is that excess of chlorine produces a characteristic unpleasant taste or odor in the water, and the excess amount of chlorine can also produces an irritation on mucous membrane. Hence, more effective it is more effective below 6.5 pH value and less effective at higher pH. The break point of chlorination. It is also called as free residual chlorination. The breakpoint of chlorination gives the exact addition of sufficient amount of chlorine to oxidize the organic matter, reduce the substance, and remove the free ammonia in raw water, leaving behind mainly free chlorine which possesses disinfecting action against the diseases producing bacteria. Hence, the breakpoint of chlorination of water is defined as the chlorination to such an extent such that the microorganisms as well as the bad taste and odor present in the water are. And the fourth stage is free residual chlorine. Advantages of breakpoint of chlorination. It oxidizes completely the organic compound ammonia and other reducing compound. It removes color in water due to presence of organic matter. It destroys completely all the diseases producing bacteria. It removes both odor and taste from the water. It prevents the growth of any weed in water. Another method of chlorination is by using chloramine. When chloramine and ammonia are reacted in the ratio of 2:1 by volume, then chloramine is formed. Chloramine is much more lasting than better bactericidal than chlorine alone. Chlorine when reacts with ammonia will form chloramine with small amount of HCl, and this chloramine tablet when added to water it will form a disinfected hypochlorite in the water which will generate the nascent oxygen and kills the germs and bacteria forming ammonia also. Disinfection by ozone layer. Ozone is an excellent disinfectant which is passed in water by passing electric discharge through cold and dry oxygen. Ozone is highly unstable and reactive and breaks down the liberating nascent oxygen. The nascent oxygen produced is a very powerful oxidizing agent and kills the bacteria as well as oxidizes the organic matter present in the water. For example, here it is oxygen ozone O3. With the help of radiation, the bond is broken and there is a formation of nascent oxygen. The contact period is about 10 to 15 minutes in sterilizing tank and the usual dose strength is 2 to 3 ppm. Hence, the ozone that is O3 is break down with the help of radiation into O2 plus O which is nascent oxygen And this nascent oxygen is responsible for killing the germs and bacteria in the water. The ozone is generated from oxygen by UV light or an electrical discharge. As oxygen passes through the UV light or electrical field, the oxygen, that is O2 molecule, separates to form two oxygen atoms. Hence, the unstable single oxygen atom combines with an oxygen molecule to form ozone. This is the formation of ozone. As the oxidation process takes place, the additional oxygen atom is consumed, leaving only oxygen behind. And as the ozone molecule contacts a microbe or the other contaminant, the microbe is destroyed and the other contaminants are also. The advantage of this is that it removes the color, odor and taste without giving any residue, and if it is in excess, then it is not harmful since it is unstable and decomposes into oxygen. The disadvantage is that it is quite expensive and costlier than chlorine and cannot be employed for disinfection of municipal water supply.